As our last guest speaker of the day, we welcome Professor Caroline McMillen, the Chief Scientist for South Australia. Professor Caroline McMillen commenced in the role of Chief Scientist in October 2018 after serving as Vice-Chancellor of the University of Newcastle for 7 years. She was appointed an Officer of the Order of Australia in 2020, awarded an honorary doctorate by the University of Adelaide in 2019, and was elected as a Fellow of the Australian Academy of Health and Medical Sciences and a Bragg member of the Royal Institution Australia in 2015. Professor McMillen was also honoured at the end of her term as Vice-Chancellor to be presented with the Key to the City of Newcastle by the Lord Mayor, in recognition of her leadership contribution to Newcastle and the region. Professor McMillen is also an active champion for science and science education, for the next generation of scientists, and particularly for girls and women in science. She was a member of the Expert Advisory Group for Science in Australia Gender Equity, which played a key role in the introduction of the Athena Swan Awards in Australia. Throughout her career, Professor McMillen has been committed to building collaborations between universities, government, industry, and communities that drive innovation and have a positive impact on the economic, environmental, social, and cultural health of Australia. Welcome, Professor McMillen.
Thank you so much. Thank you. Thank you very much indeed. I was just explaining that I get so much more from the opportunity to consider key issues through the lens of listening more than I do speaking. What I was really pleased to do was accept this invitation for two reasons. One, I really think that this consortium has worked to maximise the value of what a consortium can be. That bringing together of expert knowledge, of course, with good collaborators, is the lifeblood of all good researchers and innovators. But to build a consortium requires a deal of energy in ensuring that as a consortium in areas of which you may not be familiar, that you are, as a leader and as leaders, maximising the impact in areas that might have been previously unfamiliar to you. So bringing collaboration together with industry in areas of critical need for the state, and we'll talk globally, and to have that model and to see outputs first and then outcomes, is something that is extremely valuable to a chief scientist who is currently charged to bring together a whole of state research and innovation plan. And so these elements of what makes things work and be productive, build careers, and also brings industry further on the journey that they want it to make, and also they transfer their insights into that research world. So for all those reasons, that's why I accepted the opportunity. Reasonably, I wanted to put this in a context, and because I've been thinking about the challenges across the world, across Australia and within the state, as a sort of challenge framework for a research and innovation framework. We're all about responses to challenges in our world of science and innovation. I thought I'd start really in that part of the ecosystem where we saw a remarkable impact of our Intergovernment Panel on Climate Change and the Glasgow meeting, the COP meeting. Reasonably laying out what we have all been working with for some time, but actually the challenge of facing challenges that span geographic areas where borders don't matter, industry sectors who find themselves either experiencing the impact of climate change as businesses in climate-affected areas, or separately those who are trying to respond through innovation and change to those challenges. And I was I was trying to think, what's the title? So I was getting a little bit caught up in my thinking about why isn't copper a critical mineral? So I just thought I'd put that in and then have you tell me why it's not. Seemed to me everything I was reading was saying it is, and we've got this weasel words for major, key, strategic, emerging mineral. I'm sure it's very pleased about that. Anyway, so let's take that sort of overarching view. The other piece is putting this in that pull force, the economic pull force, but also the social political pull force. And the World Economic Forum does a major global risks survey. And they seek from industry leaders and from influencers, young activists, leaders and entrepreneurs, what their view is about what risks are we going to face as a planet that are in the first couple of years after you've done your survey, then a sort of a 2 to 4 year time frame, and then a 6+ time frame. Now, reasonably, you don't need to read the text on the left, but if you look at the green, they're the environmental pieces. And they are reasonably, you can see a couple of bars in that first time frame, but by the time you're getting to 6 to 10, respondents are saying these are going to be global risks that impact the planet. And reasonably, you can see climate action failure, extreme weather, biodiversity loss, natural resource crises, and human environmental damage. And so there's a continuum there. And that's a frame we know businesses are responding to. But then let's look at the societal pieces, because those reflect, and you don't need to read too much, except that basically people are worried about the risk of fragmentation and actual loss of cohesion, economic and societal cohesion for large parts and swathes of the planet, independently of economic income in the region. And then the economic impact follows. So when you read through and you spend a little bit of time with this, not only do you see the bigger picture, but you see the business impact, you see the prediction by people who are well placed to make those as significant leaders, what they consider is coming. And so reasonably, we also know that the net zero energy transition and the business imperatives are well with us. So this is even understanding that we know what we know and are showing we're prepared to act in part across different governments. And we're absolutely sure that the net zero target of reducing global carbon emissions, so that we attempt to hold that warming to 1.5, although there's pessimism about that, is now actually a core principle for business. So that pessimism is even predicting that somehow we are not going to make the journey that we anticipate making. And that there's also a real concern from within businesses, particularly in resources industry sectors, that the net zero commitments being made by the political and by local, regional voices, while the commitments are made, they're actually outpacing as commitments that formation of supply chains, market mechanisms, new models for financing that have to be built or have to have been being built, and other solutions and structures that businesses with long time constants for their value chains and supply chains, which resources is, can actually meet the requirements of the decarbonisation pathway. And reasonably, that unique challenge is that need to increase further the innovation in an innovative industry sector and rebuild growth agendas. So we are in a scrambling mode, I think, is what the risk analysis says. And whether it's because we are late to the table or we're simply working at different speeds across different industry sectors, geographies and economies, nevertheless the impact is there. So reasonably, one of the impacts here that we would want to address is, well, how are we going to deal with it? And as usual, reasonably, it's good old science and innovation comes to the table. We are there, but it comes with partners. It's a collaboration. So facing these challenges, we see a large intent in science, innovation, technology policy and investment in Australia and well beyond, both on prevention, how to limit the climate change, and response, how to generate the solutions to multiple energy societal challenges. So that's where we changed the story from one of observing to one of action. Now, I think what's really been impressed me actually in the last year or so, that leading economic commentators are talking about agendas that require growth. That's growth at a company level, that's GDP or productivity growth at a country level, and that increased prosperity has to be redistributed in a different way. The outcomes of sustainability are no longer talked about as opposition to growth, so that addressing the challenge is a shared effort. But more interestingly, while both sectors of industry and across different industries, across whole regions of the world who are no longer going to accept supply chains that are not accredited in terms of their carbon or what I might call their energy costs. So growth and sustainability are moving more in lockstep with each other, shared business models, but inclusion and equity and equitable prosperity has leapt into the debate and discussion, even in places like the strategic and corporate finance practice of McKinsey, because of that risk predicted and because the pandemic gave us a sense of what happens globally when we hit a major challenge and how it impacts in one part of the world and the supply chain, the whole logistics framework for Australia. We never had the phrase sovereign capability until we saw the impact of disruption of that societal impact. So growth, sustainability and inclusion are now making their way through into the plans of nations. So coming down from that world challenge level, reasonably, this is nothing that this audience doesn't know, but of course, the raw materials challenge, and there's an enormous amount in the Copper to the World meeting, and Yi Zhu, the expert commentator from Bloomberg, and a range of commentators predicting the impact of the growth curve in need and use and the supply curve in terms of business models and the ability in terms of volatility in markets and in supply chains to be able to work to the drum required. Now, I like this piece here because it says if technology transition were to happen, there's net zero transition as expected today, what would the supply growth need to accelerate significantly in terms of, so if we looked at the supply growth between 2020 and 30 and compared it to the change that occurred between 2010 and 20, what would that be? Now, when we look here, we can see lithium right out on its own. That's a pretty impressive growth in supply required if we are to meet actually the commitments to deliver on the global action in net zero as outlined by many governments. Copper doesn't look too bad. So it had a growth between the open circle between 2010 and 20 above its baseline times, and then the little dark circle is what it would need for 2030. So, you know, against the lithium curve, not so out there, except that when you look across all of the uses of copper, for which you're all well across, whether you're talking across in the electricity networks or across in the EVs, the actual numbers begin to challenge. And so we have different estimates of copper demand exceeding current supply by about 5 to 8 million metric tonnes. That's slightly more than the Bloomberg estimate. So depends on the volatility in the dynamics of the data. Incentives for new supply growth are going to be essential and necessary, and there's a huge amount projected for the cumulative capital expenditure, both to grow and replace, depletion of capacity. And while there's relatively large pipeline of projects, the efforts to reduce capital and operating costs, it's not actually what you call trivial. So incentives for new supply growth will be necessary. And this is where we begin to think. I quite like the piece. Let me just see if I go backwards. Yes, I like the piece, that little bar over there, which says may require significant substitution. You know, yes, we'll just put that in. People will get on with that. That'll be a PRIF consortium. Requires significant substitution. Yes, where are we going to find that? Are we going to actually bring about new advanced materials, or are we going to do recycling? How does that failure to meet the demand, how's that responded in the innovation domain? So when we take growth, sustainability and inclusion as the key drivers, and when we take key challenges, what we're aware that our ability to drive change, to get that innovation in our practice, whether it's industry, deriving its innovation from within the business, or in partnerships as in a PRIF consortium with key partners who have often been in industry themselves and are working significantly at a sort of global level of innovation. So how and in what way does a lot of that innovation manifest itself? If you look at the OECD, basically about 50% of GDP growth, 50% of multi-factor productivity is attributed to innovation, and a large component of that is attributed to new technologies. Not surprising given the technology curve we've been on. And it's at the ability of companies to take up technology that leaders, and we've got significant leaders in the resources sector, are often always leading into that new technology. As they pick it up, it becomes much more likely it diffuses to smaller companies, and then it becomes possible that SMEs may or may not intersect with that in time to have the benefit for their own balance sheet and sustainability. So productivity growth occurs at that global frontier of technological change, no surprise in this room. And you really only get that benefit if you're below that technology frontier. Once actually you tend to wait as an SME till it's been made a bit bespoke to your own need, until you can see that it is working. And that's a big issue for the state. We're trying to close that gap, and we'll talk about how and why. But the basic message here is new technologies drive the innovation that we're interested in. World Economic Forum, every year, 10 emerging technologies have to, I think, add 750 billion to market capitalisation in 3 years' time from them announcing the actual technology, and reasonably have to, it's a year's panel beating. If you go back and look at these 10, 3 to 5 years after they've been announced, they are present driving the sectors. So new decarbonisation technologies and green ammonia using hydrogen came up last year. So it's not long now, and we will see that come through, and that may indeed then contribute well to the curve that we're seeing in terms of the ability to respond well to both the energy transition, because companies need to be able to market their own minerals through to markets that are seeking all of the information businesses know is required and is progressively being put into formal accreditation frameworks. And boards now are focusing on ESG frameworks in a serious manner, as distinct from a slightly hand-waving approach. And resources industry is one where that is always a serious issue. So that's the sort of global framework. Within Australia, what we've done is also set challenge frameworks, and we've set them through the National Research Infrastructure Roadmap in those priority industry sectors, and the challenge of developing new technologies and improved processing for resources and critical minerals processing is being significantly called out. in terms of what's required to reduce costs, obviously, of extraction, facilitate the project development investment, generate projects based on recovery of critical minerals, unconventional sources, and improve environmental impact. Now, that sets a challenge framework for investment of about it's about 2.8 billion in national research infrastructure. Predominantly, we've been used to that through the NCRIS facilities, and 1.9 billion of the 2.8 is for step change. So this is going to be a strong guide to the research and industry community about investment in major infrastructure. So that's the first thing. Recycling and clean energy, these are two energy sectors that are going hand in glove, as it were. The challenges here are reasonably about the future demand whilst avoiding the carbon emissions. I know so I never say coal. Anyway, it includes existing primary energy sources, of course, the renewables, and of course, hydrogen, the big call out. This is the moment for hydrogen. And taking advantage for the clean hydrogen, those of you who were at the hydrogen conference, saw that demand through the repeated expressions of interest through global players, the UK, Germany, and then across into Asia. And so what we're seeing here is this is the challenge. And again, the investment comes to meet that challenge. So we're seeing a pivoting of major infrastructure, which is driving through technology, changes within and for industry and within and for the research and innovation environment. And this state has got leaders in NCRIS, has got the ability repeatedly to show in the resources sector and the energy sector that it can add value through the NCRIS structure. So it's a lead rather than a lag. The blueprint for critical technologies, you've all seen 63 technologies. We could do the exam now to see how many you've got. Just maybe asking. We could start at the front, then we could just go around. So reasonably, these technologies called out to address the challenges. Now, infrastructure and technology, there's a bit of yin and yang. They come together, and we've actually got a major research and technology infrastructure steering group because they often work hand in glove and they're often codependent. Those areas that you see and how they break down into these are the separate major 7 categories into the 63 actual sort of technologies. In a way, we've been used to always thinking within our box of, if I'm a biologist, I'm not thinking of quantum. Why do I think about quantum? I mean, that's something to do with engineers and stuff. And it's very small. So actually, what we're now seeing are use cases across each of these critical technology areas in most industry sectors. When we ran the quantum industrial applications of quantum forum, the use cases that some partners, our IBM partners, were most excited by were in health, clinical health. So what we often see is something on the periphery becoming actually then brought into our sphere and found to be useful. You will see that across the critical technologies, and these are the priorities called by the government out of the 63, that's the prior government. So at the moment, it seems to be on the new government website, so which would seem sensible. And what you can see through those priorities is, of course, the low emissions, alternative fuels, the critical minerals strategy, critical minerals extraction and processing leading to the critical minerals strategy. So that's an important piece. And then there's a series of investments. So we've got blueprint for critical technologies, we've got a critical minerals strategy. And, if you're me and you're trying to find your way as a chief scientist, critical sounds like it's really important. And maybe that's a good enough definition. Copper seems to be right at the heart and hub of our ability to move forward in renewable energy generation and carrying the power. So critical technologies, in my, small brain, if it's required, if it's key, if it's major, it sounds critical to me. But critical technologies are actually not defined by that. They're current or emerging technologies that are fundamental, obviously, to our prosperity, cohesion, and security, which copper would be, but they face an increasing focus of geopolitical competition, or indeed a risk of geopolitical supply chain disruption. So to be critical, you have to be sort of on the critical list, and the critical list being you're not quite on the drip with the wired up to machines, but there's a significant risk for the country in terms of the actual way in which the supply chains are going to run. Their management, in terms of critical technologies, requires transparent and resilient supply chains, and critical technologies, by and large, require access to critical minerals. So that's the partnership there. Now, critical minerals are minerals which are essential for the functioning of critical technologies. That's very good, define it by another need, but also our economy and also our national security. And they are those that face a risk that their supply chain could be disrupted, which is why copper does not seem to place itself on that list, while we have a lot of it. But if you have a strong need, if you have a disruption within supply chains, then presumably that definitional framework would change. However, does it matter, is you'd have to ask, given that everyone is aware that it is actually fairly important. And I like the language in the critical minerals extraction and processing part of the critical technologies roadmap, which says that Australia is one of the principal producers of several key major mineral commodities. Not critical, but they're key and they're major. And copper is, of course, one of those. So that's the balance that is played. Critical minerals extraction and processing, the key sectors, all of the key sectors. Economic prosperity, national security rated high, as we know. So we're seeing challenge frameworks, we're seeing world frameworks being cast in to grapple with the importance of these technologies and minerals, and we're seeing Australia respond, and then we have to look to the state for its response. But there are other technologies available to us, which are also critical, which begin to come from the periphery of our vision, a bit closer to the middle. We know that mining applications for quantum, it can include use of quantum-based sensors, logistics in terms of large, complex data sets. We only need a few qubits to get some good use cases to work at scale and complexity with quantum, even before we get to the full quantum computer. You get encryption, you get security. So we're beginning to see, and the distributed ledger system, we're beginning to see this move again from periphery of vision to companies here now working in Adelaide, working in Australia, who bring some value to use cases from the resources sector. And so you might see quantum or quantum sensors being across resources, medtech, and the environment in terms of greenhouse gas detection. So these critical technologies begin to become diffused across industry sectors, which become very adept usually at understanding the particular value they have. I wanted to just say this one, I saw it's in University of Birmingham, it was in Nature this year. And basically, as I understand it, it is how you actually get over using something which is called gravity cartography. I do apologise if this is your key field. Anyway, so to actually resolve a long way down under certain features where you're going to need a lot of measurement time to just remove some of the basic noise that's coming through, and there's a limitation into how well that will give you the readings that you require for underground work or to know what is underground. And that this has been overcome through realising a practical quantum gravity gradient sensor. It took up a huge amount of press, actually, and reasonably is clearly the beginning of an interest. And I think Oz Minerals and the University of Birmingham are partners. And the ability here is obviously the beginning of a journey to move forwards this capability in quantum sensing. We won't go through advanced materials. What I like is seeing the wave come through of the research. I happen for my sins to talk to the National group of advanced materials, and they were very generous, and I learned a lot from them. But what I like seeing come through is the research growth that's being pulled forward by the need, that need in new technology to address each of these systems that need to be changed through the energy generation, storage, the hydrogen curve. We see this being pulled through with new advanced materials. This is a number of research publications in the world in each of those areas. We did that in our office because we were sort of interested in, is the research world really rising to a challenge, which would tell us it's a challenge, and I think that reinforces it. So the advanced materials applications, again, are also in the list of critical technologies and something that Australia is well placed to look at. Copper, well, what you begin to play with here is what does the future look like in terms of harnessing the juxtaposition of critical technologies, national research infrastructure capability. AI is now old hat because we all think of it just as being part of our lexicon and workflow. But how do we bring in continuous flow, chemical synthesis, distributed ledgers? So this is just sort of doing a nice random mashup to think through the change in energy and the change in technologies, driving innovation, driving productivity, and being resilient against some of the supply chain issues or indeed the business shocks that have come in rapid movement of supply chains. I won't go through that. So just finally, two sides, I think. One is, for me, the PRIF Consortium and looking at unlocking complex resources is fundamentally unlocking growth, sustainability and inclusion. Now, the elements of that I can be nicely challenged on, but it's a good view, so possibly go with it. But reasonably, what you've got is that evidence of getting productivity gains that come through the work that is optimizing something of key importance through every part of a disciplinary field and sector that can get that interoperability, that efficiency and the energy parameters and the innovation that generates. So you're combining inputs and you're having to combine it because you're across fields and new ideas that come from outside your field. You've got technological breakthroughs, and then you can get augmented business models. Research plus collaboration plus technology. And we're going to keep seeing that recipe. It's a tried and true for 3 to 4 decades, and many would argue before then, but it's just become in the OECD, the EU, the Innovate UK. They've actually kicked the tires on that. That's the inputs to drive the innovation and, importantly, the translation to give you outputs and productivity. And the evidence is beautifully defined over those 3 decades, so we don't have to hand wave about it. So transforming the production of goods and services, fostering economic growth, and in the context of regional South Australia, where our resources industries are sited, then you're getting technology diffusion, you're getting an increase in skilled workforce and inclusivity in the communities there. So I think in the big picture, this is a very clear part of a key microcosm. So how does that help a chief scientist begin to think? Begin is the word here. When you begin to think about a plan, you're wanting to know what you're addressing, the challenge framework. They're global. We've said that. And I've deliberately started global, come national, and then we come into South Australia. Because in our world, you can't address local problems where there are global solutions, and you can bring local solutions to global problems. But you want the challenge framework, and you want it validated by those who have placed their careers into a space to be able to be clear about what's oft talked about isn't an issue, and what is rarely talked about and will be a major challenge. That way you are ahead of a curve with good impact. So global, national and South Australia, beautiful frameworks actually laid out which allow the average chief scientist to understand it, but what you need is foresight. You need foresight from research foresight and associated strategy from an industry and innovation leadership team. These are the people who tell you it's 1 to 2 years away, it's 5 to 6 years away, it's 20 years away. Now, we all know the curve will, take off a bit quicker than that in new technology particularly, but you need the voice of where you are in maturity versus likelihood of impact. You also know the people who understand what's around the corner that nobody sees and its use. So foresight is key. Those of you who know South Korea well, they've got a remarkable process for bringing people together and hothousing foresight. It's a very scientific process worth thinking through. However, that's a key input. You need input from those of the community who understand where major research and technology infrastructure is placed in the face of key issues that address the challenge framework for South Australia and perhaps ahead of the national curve. You need to understand about the research and innovation workforce, and that's a very major question as the technology curve steepens. Our time constant for education is far longer than the time constant for uptake in new technology, and that mismatch costs us. And empowering innovation districts and neighbourhoods, if you put $4 billion into bringing component parts of an innovation ecosystem together, then activation of that ecosystem, which requires intermediaries, people willing to walk across to the industry office, willing to take industry partners in to a frontier technology capability centre so they can see the new technology, try before they buy, hear from a CEO about their use of it, then you're activating the purpose of those districts. Cannot leave capital investment just to work it out itself. And reasonably, those components, a challenge framework, a highly structured approach to addressing those challenges through the voices of those who've earned the right, as it were, to think that their contribution would reasonably be taken pretty seriously. But then what you're doing is you're building the plan, but you're making sure your inputs and your outputs are going to allow growth, going to allow sustainability, and going to allow inclusivity, because this is the state of South Australia. That's the values of the state. It has been since its foundation. It has been what has driven our renewables agenda, independently of which government, and it still is a key piece for us outside in the region as well as within Adelaide. And I should add, I think copper will be critical. There you go. Good to know.
Nuclear energy, where does that sit?
Yeah, look, I think, when you're putting challenge frameworks together, you have to keep all the solutions on the right-hand side. And then you have to simply begin to weight them, firstly, in terms of the maturity of the technology, secondly, in terms of where, and this has always been the case since Kevin's gas is pretty decent major review of the nuclear technology landscape in South Australia. So you have to determine where communities are placed. There is a sort of laser fusion technology piece which seems to be emerging through some way back. But my role, if you will, is to bring the right people together, because nothing's off the table. I think in the current world we live in, putting things off the table for whatever reason, makes sense. So, so you reasonably, sometimes there are technologies whose moment comes.
I'm interested. Yeah. Thanks for the talk, and I would have to agree, copper is going to be critical. The interesting situation we find ourselves in societally is one where in prior, Paris and Kyoto, we've gone with sort of targets we knew we had plans to meet. Coming out of Glasgow, we've gone with a target that no one's got a plan to meet.
Yes.
Could you talk about just that sort of disparity between, call it a goal or an aim or and the actual plans to get there? Because I sense a bit of cognitive dissonance around.
Yeah.
Sort of,
Look, it comes through actually independently. For you're within Australia, for which it's quite a very obvious dissonance, and it's actually coming through in other jurisdictions, because the commitment, as we said, the commitment to the net zero targets, in a sense, by some sort of, we have this human wanting to have the decade define our leadership. 2030 was what we said, or 2040, and the dissonance with business models and the rate limiting step in the resources industry, over which there may not be a control factor that can bend to the will of that target. And that there's a lot of good, reflections on that, which you will all be well aware of, on the sort of stop-start approach and the market shocks that may arise as a consequence of that. That one part of the supply chain's ready when the other isn't, or the value chain has got it ready but the supply chain isn't there. And the geopolitical pieces are reasonably drivers here. So where, if I had to reflect, where national security is important, governments tend to act to fill gaps. And by labelling, and in technical terms, I understand why any government would place critical before something as a label that was critical for national security after the pandemic, when we've seen the response we've all seen, where we weren't prepared for something that challenged globalisation. So reasonably, my view is that we've got a better handle on it now. Governments can accelerate so much, but there's actually things you can't accelerate. Put all the money in, but what you can do is buffer market shocks to some extent to allow companies the time to recover from failures in supply chains. But none of that seems to me to be highly predictable as we speak. So it seems that the world has, across the various commentators, both the industry side and in the financial commentators, have this in view. The solution would appear to be a sort of critical council, as it were. And that critical council is formed on the basis of having identified critical technologies, having identified critical minerals, because we realise these sectors are critical, that we can't have separate conversations going on across. Businesses are very adroit at having good competitor conversations and collaborating on some key issues. And this would be an issue that would capture all the lead industry. So my sense is you need a critical council, as it were, to manage as far as is possible in a collective way some of the issues which, if they are managed collectively, might blunt the shock, even if they don't remove it. So, I think so far we've had statements, because the pandemic hasn't quite left us, and because there's there's more present geopolitical challenges, particularly in the Indo-Pacific, if I might say, and so therefore you would think that this will come, but it probably won't be in the next 6 months. It'll be well thought through, and industry leaders, I think, will carry this. It just in a sense that the energy sector did, in terms of the renewable challenge, which was a similar challenge, a government who wasn't going there and then suddenly was. How do you see it?
How do I see it? I'm seeing a significant gap between the, the spokesman mouthpiece of industry. Yes. And what's actually happening on the ground.
Yeah.
They are starting to work through to having plans that they can, definitive plans they can talk to and be measured against. But the other piece is, and I think you alluded to it, different parts are in different, you know, some parts, like take renewables, are ahead of, say, where the grid is.
Yes, yes.
And the grid needs copper. So,
Yes.
so
It's critical.
we're getting all these things in sync is not going to be any easy, and the time needed, for instance, to re-engineer the grid or come up with a solution that doesn't need re-engineering the grid is, I think, longer than people think.
And it is the challenge for the 1.5 global degrees centigrade, where part of it could be argued is we had that time, and it wasn't with industry. It was certainly political kind of moving not in lockstep with government is difficult when you're in the major critical sectors. So. It is interesting. What I do find interesting, though, is the determination of Europe. Mm-hmm. Now, how this is going to hold, because if you can do that across Europe, and whether you can or not, is obviously going to be a major, from years from now, it'll be, a lesson in your MBA or your MTA, your Masters of Technology in Business Accounting, because they've set the clarity of what they're expecting, and as a market force, that's a very strong pull, and that's the conversations we go around a lot at the moment. Are those conversations, but synchronising the way forwards. That's hard. Yep. Oh.
What's your position on the role of the change of the Earth's magnetic field, which is changing and has been changing since about the mid-1990s at a rate of around about 300% more than what historical change has been?
Look, I'm not positioned to have a view on that. I'd have to have a talk with you, and you would say, this is my world. So I meet people who will say, do you know that? I'll say, nope. Let's put it in. And then my role is to try and find a frame within which it's either actually being captured and worked through in what I might call an existing way as part of a group of related areas. Solar flares was the one, actually. I was tasked, somebody told me I should be worried about solar flares, and I did say, it's a one in. The very next week on Cosmos was, this is coming. So, sometimes you have to have the good grace to say, well, there you go. So reasonably, I'm not positioned to have a view. I am positioned to find the views of others who understand the key challenge. And then where that sits on the map of impact and probability. It's a classic, it's a classic risk analysis, isn't it? The only thing is, don't forget to keep going back to the risk analysis if the data change. Because that often people go, solar flares, they're not going to happen 1 in 1,000. Well, maybe that was 1,000 years ago, but maybe now it's 3 in 50, and you can be wiped out by one. So, risk, medium, consequence, catastrophic. Yeah, probably bring it up to think about it. So I'm not being flippant. I'm actually saying there has to be a framework within which those risks are placed. And I've not been asked that before, so it's great. Yeah.
Yeah, the only ones who are doing really much work in this one, obviously, Australia's negative, but NASA has put some publications out about this because it is at least in the scientific arena, but in the, whatever you call it, the mass media, it's missing in action altogether.
Yeah,
So,
I certainly, often I get a cue from a publication, you keep trawling, obviously, and then you can put it with a few other pieces and begin to understand and go and talk to good leaders. But that's peripheral at the moment, so it's got to come more central. Still worried about solar flares, though.
So with that, we will thank Professor McMillen for her time and thank you for answering our questions. Thank you so much. Thanks for joining us today.
Often my family go, Mum, what are you talking about? And I go, oh, Mum, they come home with the chocolates and go, oh, good. Yes. This makes sense of my job.
Very good, thank you.
The astute amongst us will notice that we've had a bit of a variation from the original agenda. Apologies for that, it's been a bit of a choose your own adventure. But now we will get back to Program B of the Consortium, and we will get to Dr. Todd Gillam. Todd, you get to follow the Chief Scientist of South Australia. Todd is a postdoctoral researcher at the Future Industries Institute at the University of South Australia. Todd completed his PhD in synthetic chemistry to take up a job within the Applied Chemistry and Translational Biomaterials group, working mainly across the biomedicinal applications. Todd then worked part-time in the Surface Interactions and Soft Matter Research Group and part-time on Research Project 7 of PRIF, developing a sensor for flotation frothers. In January, Todd moved full-time onto the PRIF project. Todd presented his research at the Royal Australian Chemical Institute's National Congress earlier in July and was recently awarded a National Intelligence Postdoctoral Grant Fellowship, which he will commence next year. Additionally, Todd purchased his first home last year. So congratulations to Todd and welcome to the stage.
Hello. Thanks for warming up the crowd for me, Carolyn. It's very kind.
If you could deal with an identical question.
I could try a creative answer, but it wouldn't be a suitable answer. Okay, so I'm going to talk about monitoring froth flotation agents with inclusion complexation materials. Now, I sit within the flotation sort of grouping of Project B, and my main objective is to develop a means of having a way of measuring these things in real time. So when I say these things, I'm talking about these frother components here. They're wibbly-wobbly molecules that stick to the surface of bubbles and mediate interactions with collectors, which my understanding is they decorate the surface of high-quality sulfide ores. And this is a means of separating high-quality material from lower-quality material. This was really articulately described by Max and somewhat less articulately described by me. So my understanding of how this currently works is that this lovely froth is frothing about, and some people come up and they're like, oh, how's that going? I reckon it's fine. Well, just chuck some more frother in there just in case it's not. Now, that's an oversimplification. I don't necessarily understand the intricacies of how to judge a froth myself whilst looking at it, but I was tasked with seeing if we could develop something that gave a very acute real-time measurement of these frother mediators and how that impacts the quality of this froth and therefore sustains the recovery of these minerals at a high level without the need for overdosing and wasted addition of chemicals. So the premise behind this is to use a gravimetric sensory platform, and this entails taking a quartz crystal microbalance, which is a small crystal surface that oscillates, shimmying back and forth at a particular frequency. And as it interacts with molecules that are associated with its surface, this shimmying dampens. And with that dampening frequency, it can be correlated to a mass change in solution. When I started on this project and we looked at these target compounds, it gets a little bit hairier than this later, but these are the 4 primary candidates that we were interested in sensing. And if you look at them, they're all kind of samey. And by samey, I mean they feature hydrophobic tails or sort of head groups and hydroxyl. But there's not a lot of distinct feature to them, and there's not a lot of rigid 3-dimensional structure. So if you were to take a templating approach and make molecularly imprinted polymers like you might for pesticides or drugs that you might want to look at in biological systems, you can't really do that with these. So you have to look at a different means of handling interactions with them in order to establish that interaction on a surface. So this presented us with a bit of a different angle to take, and we started to look at cyclodextrins. Cyclodextrins are these sort of hoops made of sugars, and on the inside of the hoop it's quite a hydrophobic surface, and on the outside it's quite hydrophilic. These are used quite a lot in the development of sort of excipients, binding agents and drug delivery platforms within pharmaceutical spaces. And they have the benefit of stabilizing complexes with hydrophobic molecules by hosting them within that cavity as a guest. So they sort of whoop straight in there, and that's a pretty stable sort of complexation. So we were trying to see, well, can we use this as a basis for establishing interaction with the Froth reagents, and how can we modify materials to then adapt that onto the quartz crystal microbalance? So this is just a bit of a proof of concept slide. So how do we know that they actually associate in solution? We can use proton magnetic resonance, and won't labour this point, but we can see that key resonances associated with particular protons of the internal cavity of the cyclodextrin undergo a shift that is associated with the complexation of key components. So we screened this against what was reported to be in the interfloat mixture and things that are likely to be sort of in solution and they don't associate, and the frothers do. So the next step here was to start looking at what we could do with these sorts of materials, and I've listed some key findings here. So we've found that materials based on beta-cyclodextrin, largely sort of polymer particles here, function to absorb the components of the interfloat mixture in solution, but they were sort of a little bit large to adapt onto a surface for sensing. So we went to a smaller molecular model featuring this thiolated cyclodextrin, and currently developing that into the sensor coding to get a response to this in solution toward a real-time sensor. I'll say toward because it's not doing it yet. So to start off with, we had to take these quite water-soluble cyclodextrins, turn them into a material that can be handled in aqueous media, and measure it in some capacity. So I made these highly cross-linked polymer particles, and we had this real challenge of trying to reduce the size of these, and we got some way by using a emulsion polymerization strategy, employing lauric acid to sort of make little microenvironments for the formation of these particles. So we got these sort of particles which were not small enough, and then I desperately tried to grind them smaller in a mortar and pestle, and that was largely unsuccessful. But they did get pretty small, but not pretty small enough, and they were able to respond to the more hydrophobic components of the interfloat mixture. So what I'm showing here is that when I do gas chromatography, mass spectrometry analysis, there's a lot more in the interfloat mixture than it says on the bottle. And I identified what many of these components are, except for old mate retention time 11.07. That's a mystery. But the point here is that when I start dosing these aqueous solutions with increasing amounts of the polymer particle, I can see that there's a trend with the adsorption or binding of these components in solution that are being removed from that solution when I spin out the particles and measure it again. That correlates with increasing hydrophobicity. So we had to go to a bit of a smaller system, as the mass of these particles was just going to render the sort of QCM sensor a bit useless. So to achieve this, I took beta-cyclodextrin and I modified that hydrophilic rim around the outside. So I substituted out the primary hydroxyls for a good leaving group, bromine, and then swapped that out for these sulfhydryl groups that I've shown decorating around the outside there. And this gave sort of a very sort of brick dusty, fallout of solution, easy to handle beta-cyclodextrin derivative, and that is able to bond to a gold surface of a QCM. Now, the current challenge is building up the density of these cyclodextrins on the sensor to get a high enough response for meaningful measurements. So present direction of this research is sort of cross-linking a lattice or matrix of these on that surface to really build up a thicker brush or boundary layer that's able to improve the sensitivity of the QCM in response to the individual components of the frother mixture, and then take that on to a simulated example of the frother in solution, and then ideally demonstrate it in a replicated froth flotation setting. Beyond that, this project has sort of spun off a bunch of materials that were sort of produced in tandem and have some utility in their own right. So I'd like to sort of visit their utility in other spaces, because they do tend to bind a lot of hydrophobic components in solution. And this could be valuable for decontamination of water and soil, where the accumulation of hydrophobic components, hormones, pharmaceuticals tends to be a problem currently, and there's a lot of direction towards trying to resolve that. So lastly, I'll thank the project team, my line manager, Anton Blanco, Bill Skinner, David Beattie and Marta Krasowska, my translation partner, Chris Greet, and I've also had the pleasure of having several research placement students join me for like little projects throughout this project, and they've all been tremendously helpful. I've also got a picture there of our lab team over in the ACTB group. Thank you.
Do we have a question for Todd?
Come on. Anything.
Oh, hang on, Nigel, sorry. No?
These are standby questions. Questions have priority.
Just, yeah.
So I think I'm understanding this right, correct me if I'm wrong. So you coat your little gravity vibrator thing, it grabs the frother.
Yeah.
And then that's a one use. You put it in there, it's then full because your binder's so good at binding it.
It should be a somewhat dynamic process.
Okay.
So for instance, when we take the polymer particles, we are able to leach things back off of them. So it is somewhat concentration dependent and driven by equilibrium of binding and unbinding. So it's a dynamic sorption characteristic, because they're not chemi-sorbed, they're not covalently bound.
They're just stuck in the hole.
They're stuck in the hole, but they can come out of the hole. There is some equilibrium involved there. And that's how these are used primarily in drug release, is they delay or slow the release profile of a lot of hydrophobic molecules that are difficult to solubilize, and that's their benefit in that arena.
I love what you've done. It's really cool. I love the crossover from the drug space.
Thank you. Cheers.
We wrap up Program B with Dr. Richmond Asamoah, a research fellow at the Future Industries Institute at the University of South Australia. Richmond is conducting 5 translation projects and supervises 2 research projects. Richmond has over 12 years of in-depth knowledge and hands-on experience in mineral processing and extractive metallurgy. He holds a Bachelor of Science in Minerals Engineering and a PhD in Resource Engineering, obtained from the University of Mines and Technology in Ghana and the University of South Australia, respectively. In the past 3.5 years, Richmond has authored and co-authored over 50 articles published in high-quality journals and conference proceedings. Richmond and his colleagues were recently awarded the Australia-India Strategic Research Fund for recovering battery materials and rare earth elements using advanced technologies. Along with his giant list of achievements, Richmond has also recently welcomed a handsome new baby boy into the world. Congratulations, Richmond.
Thank you very much. He's turning 2, so he's well within PRIF. Today, my talk will be on the translation projects. Talk to you a little bit about how they are related with the research projects and some of the benefits and opportunities we begin to see when we translate some of the solutions that we're finding out from the excellent talks that you've heard today. So in Program B, we have 5 translation projects. And these projects have been linked with the research projects in 2 ways, forward and backward. So looking back at each research project, providing support to the research project, that is giving them the necessary data, the equipment that are required to make the project successful, and also advice to make the project more strategic to address key industry challenges. But also at the same time, looking forward, where we try to take some of the excellent outcomes, as has been shared today, to the industry, see how we can begin to implement or try to put in necessary activities to implement those technologies. An example is looking at the first 2, which is Translation Project 7 and 8, which is a Manta mic acoustic analyzer. And as you've heard today with the acoustic sensor, we try to undertake a study on site to assess where we can install these sensors on plant. Again, looking at MagoPop, we investigated a location where we can install the sensor and also install that, collect data to help with research project 4, as you've heard today. And the translation project 10, a new morph sensor which can be used in a tail slit circuit to monitor ferric ion concentration. That is very important in monitoring or detecting quick gel processes, which is very critical. And again, for the translation project 11, particularly building or fabricating a laboratory mill, which can help research project 1, Kweku, as you've heard today. So in all these activities, there are key findings that we begin to see, which I'd like to share with you. And it became apparent that it's possible to push the current process boundaries a little bit further to maximize performance of the operation. And that is being able to produce more from the less resources that we have, being able to increase the mill throughput within constraints of mineral liberation. But 2, to maximize the operational stability, having more stable operation, a more reliable, available unit operation, through combination of process predictions or predictive maintenance, as was shared earlier. And some of the solutions that we're beginning to see from the PRIF can address the key ESG challenges, which was shared at the beginning as very critical to the mining industry today. So very useful for safer operations, particularly looking at the tail slit, where we are trying to avoid challenges like gelling, which is a safety issue, but also being able to maximize the uranium extraction. Now, why is this very important? We see that the demand for copper is increasing. And when you look at the chart on your left, the left corner there, we see that the copper that we need in the next few years, 2050, is over 5 times what we need today. So we need to be able to produce more copper. But on the flip side, the grades of copper in our resources are decreasing. And so in a few years back, where you have grades as high as 20%, that means that for every 100 grams of material, you can get 20 grams of copper. In the next century, we're seeing values as low as 0.2, which means that it has reduced 100 times, where we are only getting about 0.2 grams of copper from that resource. So we need to find and improved ways of extracting copper. And that also starts with our current processes, our current unit operations, how to maximize the efficiency and get more copper from the operation. So when we look at our current operations, as has been shared, makes it very easy for me to talk about it, because Max mentioned that most critical parameters that are to be measured in flotation circuit are, for instance, not measured. And these parameters, not only in the flotation circuit, but also in the grinding circuit, make it very difficult to integrate the various operations, unit operations together to help each section be aware in advance of what is coming its way and be prepared to make necessary adjustments to maximize performance. So this is a key challenge that will be very important to address, getting all the unit operations to talk to maximize the extraction performance. And that is what we begin to see when we implement the solutions that has been shared from the research point of view today. So taking you through the research solutions and also what we've done at the translation partner point of view, looking particularly at the communication solutions, we have, as shared, an acoustic sensor which can be able to detect the feed variability in real time. Now, this is very important because in cases where you have significant variability in the ore, the control mechanism is conservative. So you are not able to maximize the extraction, and you have to be very careful not to flip into the unstable regime, which produces unuseful or not very effective or good products for the downstream operation, and absolute waste of energy. So you want to be in the stable regime, and a typical approach there is to therefore reduce the set point, not being at the optimum maximum point, which is well known as the best point to maximize energy efficiency. You become a bit more conservative and you operate at those red dot points. And that is understandable. It's because of the risks that is associated with moving on to the very high point. But with a sensor which can help us detect when the feed in the mill has changed in real time, we are giving the operator or the control room additional confidence to know when the feed in the mill has changed and make necessary adjustments to be able to keep the maximum performance high. So for translation activity, we've been able to identify locations on site, particularly BHP Olympic Dam, where these sensors can be installed, and that is looking at the Spadella mill. And also, as shared with accelerometer mill, this is very important because that is feeding directly into the productivity of the mill. That is, we knowing when, say, a liner is failing, and as we know, as the liner even wears off, it affects the production curve as well. So getting this information fed in real time is very important. Now, with the hydrocyclone, a lot has been said about it. I won't talk too much about it. Classical issue being the roping, where the coarse particles and the fine particles miss path. But also, the activity that Difan talked about as a future step where he can be able to monitor the distribution of the curve is very important because on plants, a fixed figure is looked at, as is mentioned, P80, 75, for example. But we can see that you can have a P80 value of 75 microns for two different streams and have different distribution for the product. And in the flotation circuit, that will show different response because we know the fine particles float differently to the coarse particles. So that's very important to be able to get those additional fundamental information being implemented on plant side. Going to the flotation circuit, we have been able to install, with the help with Magatoy, these projects, all these translation projects are led by our translation partners. So we've been able to install the Magopop on site and have collected data from the sensor, which has been used to develop models. Now, the model that has been developed in a predictive model developed first to detect when there is a change in mineralogy of the flotation circuit. So that information, for instance, can go back to feed upstream information that is coming to confirm that what is sent to the plant has changed by this. We are detecting this change, for instance. But also, with the pop chemistry information, we can predict how the recovery and grade will vary in real time. And that is important because as these figures vary, we can, based on our set point, adjust using additional optimizer, which was shared by Bismarck this afternoon, to adjust the various process variables in real time, the pulp chemistry, to be able to maximize our copper production. And again, looking at what Todd just talked about a few minutes ago, where we can be able to also monitor the frother and collector in real time and feed that into optimizer, saving significant amounts of reagents that are used in the frother. But we also know too much collector concentration or frother concentration going downstream has significant impact on the operation. So we need to be able to address these challenges. But these are significant solutions that we're seeing from the PRIF Consortium. For the tail sludge, we've talked about it as well from the beginning, where gelling is critical. Now, whilst ferric ion is important to dissolve uranium-4 and leach it into solution to uranium-6, so ferric ion is very important for that reaction. We know excessive amount of that same ferric ion can facilitate other reactions, like aluminosilicate reacts precipitation, which causes the gel. Now, gelling is because of a reactive gang minerals like chlorides, which are, when not well monitored, can affect the operation. So we need to have enough ferric ions in the solution, but we don't also need too much, which can affect the process. So being able to monitor that in real time is very important. A typical challenge, which specifically looking at where you can blend, putting constraints on when you have high grade copper and then there is a significant amount of high chloride, that can affect what you want to process, for example. So these models, as has been shared as well, we have been able to mathematically develop relationship between the ferric ions and the MOF sensor to show good interaction, attractive interaction, which when applied on the industry can be very useful. There's still more work to be done on this to take it to the next level. So what am I trying to talk about? When we look at all these, from the grinding to the tail sludge, we see significant benefits that can be transferred to the industry. From the grinding circuit, where we have sensors that are detecting a change in feed characteristics, these information can be sent directly to the downstream, which is the cyclone, which is focused on classification, and also to the flotation circuit, helping them to adjust their variables in real time to the changes that are coming from upstream, and the changes and the impact on the process being fed back in real time to help us maximize our copper production and maximize throughput whilst we are still reducing costs, and more importantly, maintain operational stability. Perhaps this will be your favorite slide. I don't know. Maybe you judge afterwards. We can talk about it. But when we try to use some of the models that were developed in the flotation circuit to begin to see what the benefit could be to the operation, we see that we could make about 2% increase in copper recovery when we implement that model, and up to 15% increase in throughput and 17% copper production in all. Now, this, we began to convert that into monetary terms, and we could see savings about $150 million per year, dollars. And that is very critical because this adds up to the significant water savings and energy savings that can be made. Now, this is just a representation of the kind of benefits or savings that can be made when some of the solutions that have been shared today are implemented on site. For example, in the grinding circuit, we know that we will make benefits in the increase in throughput, avoid overgrinding because we know when the coarse particles are going into the flotation circuit, and we avoid fine particles going back for overgrinding. And we are also having energy efficiency, high energy efficiency. Whilst in the tailing circuit, we are saving reagents. We are also maximizing uranium extraction whilst reducing the risks of gelling. So going forward, I look forward to being able to validate these models further and sensor on site, trying to demonstrate these values that we're seeing from the models that we've developed on site and demonstrate their benefit. And also continue to work with our translation partners and to advance the technology readiness level or commercial readiness level of these promising technologies. I would like to thank Professor Bill Skinner for significant leadership and coaching for the past 3-4 years and even throughout my PhD, and also all the program BCIs for the significant contributions, postdocs and PhD students. Our translation partners, Chris, John, significant meetings, impromptu going to sites, and out of office hours talks about project development. Thanks so much. Our end user partner, Kati, and the team, You've been fabulous for the past 4 years to help us get the data that we need and to make progress on this project. Thank you all for listening to my talk today.
Do we have any questions for Richmond?
Richmond, you mentioned $150 million of potential benefits. Is it only in Australia or globally?
So just in Australia, yes. Yeah. So that's just based on the model that I shared with you in the flotation circuit, where we can predict the amount of power recovery and optimize what should be done to maximize the operation.
Yeah, this might be for Richmond, or it might be for people like Chris, who've been mentioned a number of times here. Where we're at now with the research, and we've shown where we are in terms of the TRL scale of a bunch of this research, some of it, particularly the stuff that's been done with Magato, for example. Now I think you guys listed at 7 on the TRL scale, but Adrian talked earlier today about the commercial maturity as well. How far away do we think we are from commercial products for some of this stuff, which seems quite tangible to me now?
Yes, we already have the pulp chemistry monitor on site, and as Bismarck mentioned earlier, we're looking forward to collect additional data set from site, which can be used to improve the models that have been developed here. What we intend doing to demonstrate the value of having pulp chemistry measurement on site to BHP, show what value that is, and on the technology readiness level, that can move it to the next level. On that scale, we currently building on 7, but that's because Magato has done a lot of work in the past as well, demonstrating the value of the technology. What we want to do, we've gotten some data from Dowd, but we would like to collect more data set to prove that a bit more. Yes, and Bill's mic is up.
Oh, I was just going to add that, perhaps included in the next step might be, okay, we've got this optimizer model. Why couldn't it just be sitting separately, looking at the data coming in process control or whatever? Let's leave out the Mago pulp at the moment if it's not operating at the time, but just have a parallel prediction of what you could be producing at any given time and see where it undercuts or where it overestimates, that kind of thing. And if that's something that's sitting in the background, collecting correlation or comparative prediction versus actual performance, that would at least give some confidence as to whether that particular optimizer could be integrated to the actual process control.
Yeah. If you could test that on site, that would be really, really good.
I mean, you could do it on the computer. If you could just get the recorded data for the
collect it
period of time, and then run the optimizer over it and see, well, you could have done better there, but maybe not there.
Yeah.
Maybe that could be related back to some big change.
Yeah. Chris.
Mago pulp is a product.
Yeah.
We've got one installed on the Jamison cell at Prominent Hill. We have been waiting for 18 months to complete the trial because COVID has stopped things from, or people getting to site and various other issues. We have run a very, very short trial at Prominent Hill where with our algorithms, the pulp chemistry tells us about changes in the mineralogy, which we can then work out what collector air and level we need to add to that Jamison cell to get a particular grade at maximum recovery. and that's what we want to test in the extended trial. But we're very, very confident that measuring the chemistry, combining it with the other plant data, and using very smart mathematics and having the right algorithms, we can actually improve their grade recovery curve and reduce reagents. We've got one installed at Sunrise Dam in Western Australia. Again, COVID stopped us from moving forward. And the other thing that's stopping us over there is a shortage of people. They've had a lot of people leave. So you have a champion, they disappear, you have to go and beat somebody else up to become the new champion. We've got one at Telfer, one at Cadia. Again, we need to go and beat people up to make them champions. When you start looking at chemistry, I mean, Max said it, flotation is a chemistry thing, yet we don't measure chemistry in plants. When you look around the world, and I do travel around the world, and I'm starting to do it again, you look in Australia, people start to understand pulp chemistry. You go to Chile, there's no understanding. So we're really at the forefront of knowing about this stuff and starting to implement it. So it's the way forward. It's, in a lot of ways, it's the next step change in flotation, is measuring the chemistry. The other thing about Mago Pulp, now I'm being a salesman, it's a platform for some of these other sensors. Being able to measure collector and frother, being able to measure the metal ions in solution, that all helps us understand the surface chemistry, and then gives us an opportunity to change the strategy you're using at that particular time on that particular ore to maximise grade and recovery. Thank you for listening to me. I hope I get a bit of business.
Thank you, Richmond. We now have a little brief period of time to ask any last questions for Program B. So this is the discussion time for Program B. Nazim, do we have any online questions?
We have one question for Bismarck. Thank you for your presentation, Bismarck. What is the number of data points you used for your modeling?
Let me just answer in a generic way. We have, I showed a number of results over there, and for the results that I showed, the training data set consisted of at least 44,000 observations, which was taken from a span of 6 years. But for the model that included the pulp chemistry was only for 3 weeks, and it was about 315 observations. I hope that answers the question.
Do we have any last questions from the room?
I'd just like to ask Todd.
Hang on, Nigel, we'll just get the microphone to you so our online audience can hear.
I was just going to ask Todd that question I was going to ask him before. What is it going to take in your case to drag your project's TRL over towards the right? What do you need?
Is this on? I don't think it's an issue of money necessarily, like touche. If you were to get someone else working on this ongoingly, then yes, you would need to employ them. But what it is for me is we started off on this project like trying to eat soup with a fork, and now we have a spoon. But that spoon's probably just not big enough. So what I'm trying to do is like build up that capacity on the sensor to improve response. I think I've got a pathway forward with that. I've started synthesizing cross-linking components to try and build up that surface. If that surface is built up and I can prove the principle in the next few months, I would say that that would take the technology readiness forward. That said, though, it will be an iterative process of doing it, trying it, and seeing what I need to tweak.
And it will go still faster if somebody gives you suitcases full of money, yeah?
I mean, undoubtedly. But yeah, just trying things and getting through things faster is the challenge.
Thank you.
Okay, thank you to those who spoke in Program A, and thank you for the questions and contribution from the audience. Last speaker of the day, before we go to our wrap-up session, is Gavin Yeates. Gavin is the chair of the PRIF Consortium Governing Board. Gavin is a mining futurist at Gavin Yeates Consulting with over 35 years of industry leadership and experience. Gavin is an established executive and leader in strategy and technology. He is environmentally astute and is able to provide profound systematic context to how strategy should be considered and formulated. In addition to being a subject matter expert in mining and technology, he is passionate about helping client organisations leverage technology into their businesses so that their strategic intentions are realised. He has a track record of developing, delivering and implementing strategy through aligning and empowering stakeholders to deliver profound change to organisations. Gavin, welcome.
Thank you, and it's good to be here today and to have the opportunity for the last word. I guess as chair of the governance board, I'm in a good position to sort of reflect on the PRIF. I want to really celebrate the successes and particularly the people involved, and acknowledge some of the challenges that we've had to overcome in delivering it, but also look to the future a little bit. So if you'll indulge me just for a little while, I'll go back to, what is the PRIF? It started back in October 2017, but before that there was quite a significant effort. Steve Grano put in a lot of hours in formulating what the PRIF would look like. $14 million spent in cash and in kind, and when you look at the presentations today, you can see that $14 million has gone a long way. We've all seen the overview slide, which I think's been really good to try and bring everything together. Really loved the sort of overview type presentation like Richmond just gave us, that puts the context of the pieces of the puzzle together in the whole. So we've had the two programs focused on upstream and downstream, the 14 research projects, and we heard from Adrian Beer this morning about how unique the PRIF is in having translation projects, 11 of them embedded since day one, to take the research outcomes through to translation. And he made the comment that that was both unique and an absolute key to the success of this initiative. Something that the people in this room probably ignore totally is the collaboration between two universities. I see that as pretty unique. In fact, you sit around the table with Bill and Nigel and Peter, and there isn't a UniSA or a Adelaide Uni badge anywhere. It's there, all part of the team, shoulder to the grindstone. So I think you can pat yourselves on the back on how you've integrated across two university organisations and work together to do something special. So as we come to the conclusion of and this will be the last assembly as we wind up in February of next year, I thought it's worth us just celebrating what the PRIF has delivered, and you've seen a lot of it today. We've had over 100 registered attendees, both in the room and online today, and I think that's been a really good outcome. the project has involved a large number of experienced researchers and research students and postdoctoral. If you sort of add them all up over the life of you get to about 50, which is pretty significant. We talked about the lack of capacity and capability in the technical domains for the industry going forward, and the PRIF has really delivered in that, with both Masters, Honours and Bachelor students exposed to some of the work. And I think it was Richmond, you had the picture of some of the students that were embedded in some of the research projects, and I think that we need to do more of that sort of thing. The 17 Women in Mining Technology scholarships that were awarded by PRIF is a pretty significant contribution to diversity and equity. We talk about 135 publications that have come out of the PRIF as being a great outcome, but yes, publications are a great outcome, but and then I keep going back to Richmond's presentation, what really strikes me is the impact of the research, and that's in the dollars generated, the cost savings, the ESG outcomes, the impact on the business, both in the end users, the BHPs and the Oz Minerals, but then the ability of the translation partners, the MET sector, to onboard that research, turn it into commercial products and deliver that back to the end users. And I think that's a really unique and valuable exercise. And if we just stop at papers produced, we're really missing the boat. Taking it to that next step on impact on the industry is absolutely crucial. Just on the challenges, all of this was generated, if you think about it, we started in 2017, late 2017. Took a while to get ramped up, recruiting researchers, etc., and getting data, etc. And right at the point where we're hitting our straps on research, we had to enter into the pandemic, and a lot of the work carried out under this consortium was carried out in the environment of lockdowns and the global pandemic. So I think it's worth just recognising the challenges that have had to be overcome, and we were hearing it just then of the inability to get to sites and finish trials and those sorts of things. COVID did create a challenge for undertaking collaborative research when you're in lockdown. But the success of a consortium like this really comes down to the people. And I really wanted to take this opportunity to mention just a few of those, and apologies to those I'll miss, because inevitably in these sorts of things you miss people. But it's been a great effort. I first wanted to pay attention to the governance board, which I chaired. That's been made up of people representing different sectors. And from the end user perspective, there was representatives from BHP, Kathy, who we've heard from today, and she's been a great supporter of research in the mining industry, along with Jessica and Kavita from BHP, and also Brett Trifford from Oz Minerals. Representing the translation partners, Ben Kosh and John Karageorgis from Eka and Magato, respectively. That's been really good to have them in the room and discussing the strategic direction of the PRIF. And then we've had representatives from government, Adam Forbes and David Treasure, representing the South Australian government. The board is a voluntary body. No one gets paid to be on the board. It's giving up your precious time to come and provide a level of strategic leadership and oversight. And so for those members, thank you for the time that you've given into of your own time really to be part of that governance board over the last 5 years or so. As I mentioned before, the original concept and early engagement in PRIF was undertaken by Steve Grano, who should be acknowledged for his vision and the work he did in setting it up. But throughout the life of PRIF, the leadership's been undertaken, and I'd use the analogy of the captain of the ship steering it very calmly through some torrid waters has been Nigel, and he's been, for me, the steady hand on the tiller, making sure that the direction is maintained, even though we were throwing up a number of adversities along the way. I think Nigel's displayed immense patience and calmness and resilience to lead the team through that period. I want to pay special mention to Tatiana and her management of the project. I'd have to say it's been one of the best run programs of projects where each project is well understood, the budget is well articulated, and we've gradually, as we've gone through, improved the reporting, and you know, you can see from the TRL slides you've seen today, not just, you know, are we spending the money at the right rate and got the budget under control, but we also know where the outcomes are and where our challenges are. So Tatiana's been the horsepower behind that, all that reporting and reporting to the state government on their KPIs that we committed to at the start. So thanks, Tatiana, for all of your work in organising us as a board as well. The researchers, and I won't mention them all, but particularly Bill Skinner and Richmond, who have been regular attendees at the board, and from UniSA, and Peter Dowd from Adelaide Uni. They've been about delivering the work, and again, facing into some of the challenges that we've had, both in things like recruitment, particularly in an environment where you can't fly around the world, and limits on immigration and these things. So thanks to them for their both dedication, but also the enthusiasm and excellence and the collaboration that I mentioned earlier. The annual reviews were part of this exercise, and I found it incredibly valuable. Each year of the PRIF, we've sat down and had a review about the middle of the year, and Carolyn, who you just heard from, along with Paul Heathersay, have been our review committee, and they've been hugely constructive. They've challenged us, and I hope you can see, Carolyn, that when you ask a question about how are we taking these projects through to translation, that question has prompted us to go away and deliver the program in such a way, with monitoring TRLs, involving translation partners, and then I think Nigel's recent initiative with having a legacy group looking at how we take these through to commercialisation is a direct result of the sort of questions the review asked us, and then we moved on and said, okay, that's a really good question. How do we respond to that? So thank you for spending the time in that review, because I'd have to say, as a review process, it was also enjoyable. So thank you for that. One of the, and I'll now want to sort of look forward, and yes, we've got a legacy group looking at how do we continue the work to take the good research outcomes, and you've seen where they are on the TRL path, to move them into commercialisation. So that's making something out of the existing projects in PRIF. But the last review we had, we also talked about, well, we've got this capacity and this capability built up. How do we take that to the next level? And out of that was born the thinking around the Copper for Tomorrow CRC. So this is taking what we started with PRIF and taking it to another level. How do we fund that? The CRC program is one method of funding, but the world moved on during PRIF, and Carolyn, I think copper became more critical. The copper problem has really landed in our lap, and you know we've seen the pictures of the demand for copper. We're seeing it doubling in the next probably 15 or so years. That's coming at a time when our grades are declining. How to continue to meet that demand from a dwindling supply will require some technology shifts, and those technology shifts won't be just in need to be in improving performance. It will need to be dramatic change in cost of production, capital of production, but also in ESG, because as Richmond just showed really nicely, for every tonne of dirt we'll be processing, we'll be getting less copper, but using more water, more energy. So we need a seismic shift in our approach to producing copper. And even the International Energy Agency are predicting that access to metals, particularly copper, will constrain the world's move to decarbonise. So that's the industry problem. It's great to look at it from, you know, a research problem. The other way to look at it is actually from I guess through the lens of national and state, how the governments might see that. And one way you could do that was, if you look at the current published resources in the world, Australia ranks about third in the table of national resources. If we stack up our production, we're about seventh. And if you home in on where are those undeveloped resources, significant proportion of them are here in South Australia. A significant proportion of them are right at the margin of economics. So a small change to the economics will make them able to be brought to production, and just a simple goal to have our resource production match the in-ground resource would be a massive fillip for the Australian economy. So that gives you an idea that, you know, what we're doing here does matter. And whilst we're seeing the PRIF come to an end, I hope you also can see and be excited by not just the ongoing nature of the project spinning out of the PRIF, but the opportunities that arise on looking at something bigger and longer term that may really help not just regional, local South Australia, national Australia, but a global issue. So I think if you want to know more about the bid to do the Copper for Tomorrow CRC, Michael Goodsight's a good person to have a chat to. But I really have enjoyed my association with the PRIF over its time. It's been a pleasure to serve on the board, and thank you to all those that have been involved, and you should be really proud of what you've delivered. Thank you.
Thank you, Gavin. Finally, we will conclude with a wrap-up session and invite our panel members, Professor Peter Dowd, Professor Nigel Cook and Professor Bill Skinner, to a stool up the front. To a stool. Professor Nigel Cook will provide us with a few concluding remarks, and then we'll open up the floor for any final questions.
My stool is going to have to wait till later. Interpret that how you like. Okay, I know we're running well late after the schedule, so I'll try to keep this really, really short. I'd like first of all to thank all of our presenters today. Thank you to the sponsors of the PRIF Consortium, to our end user companies, all the translation partners. Your input, your time and your know-how really has been invaluable for achieving the results that have been on show today. I'd like to say what a pleasure it's been for me personally to work with such a group of inspired and inspiring young people who have seized the opportunity to develop these exciting transdisciplinary projects. They've had to learn an awful lot out of their comfort zone, and who in doing so have become experts in their fields. It's so great to see many of you complete your research and go on to continue a career based on what you've learned while with us in the PRIF. The PRIF Consortium has had many achievements, and we're here today to celebrate them. We're proud of having provided solutions that can assist the minerals industry, enable cost savings, or in some cases provide a foundation for future avenues of research. We can be proud of those large number of journal papers. I know it's not all, Gavin, but for all of those young researchers, they are going to get their jobs in academia based upon those journal publications. They are important. All the PhD completions, all the conference presentations that have come out of the consortium as well. Our young researchers have been presenting their results far and wide and are now all very accomplished public speakers as a result. And a big shout out also to Damia for all the training sessions that she's given us over the last couple of years. Incredibly important. So the consortium has contributed to place Adelaide and its 2 collaborating universities at the forefront of interdisciplinary research with and for the minerals industry. And the success of the PRIF really follows on from several other projects in the past and will only accelerate in the future through, for example, the ARC Training Centre for Integrated Operations, which is going to use some of the PRIF data and technology, such as the SAG mill data, and it will continue to be a point of contact for some of the shared industry partners that we're working with. Other PRIF outcomes will be continued within future joint ventures under development, like the Copper for Tomorrow CRC, which are going to build on the proven expertise of our investigators in this research infrastructure and network that's been built up here, which is really almost second to none in Australia, and is proving time and time again its competitiveness in securing funding, delivering results, and profiling itself internationally. Applied research, though, doesn't stop with telling the world about how good it is and speculating about the real cost savings or additional revenue that it may bring. As has been said many times today, the consortium is now busy establishing which of the project outcomes could be implemented by the end users, which have the potential for advanced development and commercialization at some point in the future. Our researchers have been assessing their TRLs and their CRLs, the commercialization readiness levels as well, of their innovations and inventions. We're really mindful of how challenging this can be, and we've heard of that several times today. And we now have this legacy group established involving our industry partners, the Met sector, and other experienced advisors to understand how this can be realised and what is needed to ensure that the great research not only finds a home, perhaps in an existing project, perhaps in a new one, but also those champions willing to take it further, the champions that Chris has repeatedly told us about are the absolute key to success in this area. We want our outputs to result in more stable operational performance and greater profits in a sustainable industry environment that uses less resources and helps achieve those ESG targets. Even better would be if we can install and integrate all of these solutions under an ESG-driven framework, such as that being proposed for the Cooperative Tomorrow Cooperative Research Centre. So although the PRIF Consortium will be ending in just a few months' time, and we're all going to be occupied with new challenges, we want the outputs to live on. And for this reason, we want to engage with you now, in the time that's available, the audience in a discussion session, and we need your input. During the tea break earlier on, we posted a series of questions on the screen to start this discussion. We're asking which of the PRIF technologies will make a difference to your operation, which of the research outcomes that you've heard about today have potential to be used in your companies, what do you think is required to bring that research outcome to a level that would make it usable in your company, and whether in the course of the PRIF you saw any additional areas in need of sensors, data collection and integration with the value chain. So with that in mind, I'm going to ask who would like to start this discussion off, whether with a comment on a specific project or perhaps something more generic. The three of us are going to go and sit over here. To your stool. To my stool.
Go in the corner, naughty corner.
Go in the naughty corner. I don't mind talking.
We have our first question ready. We'll just wait for the speakers to get seated.
Cool. So I've got actually more, I guess, a couple of comments to make that perhaps we can reflect on as well. First comment actually builds on the end of the Chief Scientist talk and the questions that Gavin was raising about sort of the gap in capability versus what the targets may be. And what's interesting for that, I've actually just come back from Germany where we're doing some work in the energy sector. And there's some interesting challenges there that have been posed by a disruption in geopolitics in Europe, which obviously we all know about at the moment, where the targets have been set by the European Union, but there's a gap in how they're actually going to achieve that. And it's actually known because they now no longer have the supply chains that they had previously due to the conflict. And it's a unknown. They don't know how they're going to handle it, but they're trying to work out how they're going to overcome some of these problems. So I think there's some huge gaps in being able to achieve what we need to do. And I'm certainly very excited to be involved in the Copper for Tomorrow. And I really hope that kicks off because it is going to be a lot of problems that we have to try and deal with. Yeah, I think this type of environment gives a really good opportunity for developing that research and filling those gaps. And that sort of leads me into my second comment, which is just regarding the PRIF in general and hopefully what the new CRC is going to bring as well. As a METS company, we're an SME, and I find collaboration is challenging because of the limited resources we have as a small business. And I think the PRIF has been really useful in building some of those collaborations, particularly between other companies and between the research institutes. And for us, we've been involved in some of the research projects, but we've also managed to get a sale out of this. We had a successful collaboration with another one of the companies that's in the PRIF, and we are also looking at talking to various other companies that are involved. Plus, I think after today, there's certainly a few technologies that I'm interested in looking at to see whether we can develop further. So I think there's a lot of these really interesting opportunities, and this type of environment helps companies like us to kind of put this together, because if we were to try and go out and do the collaboration by ourselves, it is a really big challenge because we're resource constrained. So I think it's really commendable, and I certainly appreciate having the opportunity to be a part of it. So I don't know if there's any further comments to that, but yeah, certainly some very interesting things.
Thank you.
Do we have any other questions or comments from the audience? Oh, Ralph?
Just a lot of what I'm seeing through today is about real time, data collection, sensors and monitoring in real time, right? And I understand that because as all our sources of material come together, they all blend and we lose sense of where that happens. But I'm just wondering, through all this technology that we build, is there a pathway where we're actually simulating the whole process from extraction through to extraction before we do it. So in a mantra from our company, it is, you know, build the virtual world before we do it. So a lot of this is already after the fact. We're actually sensing the materials as it comes. So will be there a sense that we can actually build these virtual twins with all that capability and model. So if I think of, for us, we sit very much in the planning geology space. There are discrete capabilities out there that model plants, the crushing, grinding, the extraction of metals, but they're not connected to anything else. They're isolated. So you can't actually connect the planning, the resource, the uncertainty of the geology, the geometallurgy, and understand the risks around that before you do it. So we seem to be, and I may be misunderstanding this, but I feel like we're missing the potential to actually model the whole thing before we do it, understand the risks so we can then invest where we need to invest to de-risk.
I was going to throw that to Kathy because, you know, the reason being is something that she's well aware of. I mean, there's no one more knowledgeable about the mineralogy at Olympic Dam than Kathy. And if BHP had all that knowledge that you have now, when they bought it off Western Mining, would the plant be any different?
It's a lot of things are interesting in hindsight. That the flow sheet design was very robust, and it proves to be very robust as we progress to different parts of the ore body. What we haven't done a good job on is improving our sensors as we go along. So what triggered me to think about that is one of the comments that Caroline had made during her presentation, and I just actually I wrote it down here, but it was really about productivity gains versus these big, massive step changes. Frankly, the outcomes of here are all about productivity gains. You know, there's nothing in here that's really disruptive technology. That disruptive technology will change the way we think about the world, but productivity gains. And if you do little bits of productivity gains all over the place, you take your noise graphs that you had, and the importance about when we take massive noise like that and we stabilize it, you can also just raise the whole bar up. And we reduce variability, then we can raise the bar. And for us, our copper recovery is very, very high. And so increasing that bar, it's difficult, but you can still get it up. And it's all these minor things is getting a lot of things right. Number one is better sensing, and then it's having more the ability to process that information a lot better and make decisions more on the spot instead of waiting a long, long time. And I'd say so where we actually frankly get it wrong is keeping or being a lot better with the sensing side and going to digital twins. What's stopping us from digital twins is our sensing, frankly, is not up to par. You know, and so digital twins are becoming very common for plants. Back to the ore body is a little bit more difficult, but still this whole digital twin or dynamic simulation just taken to another level is out there, and we're getting pressure to do it. But most of our places, our sensors aren't where they belong. So as we go to a world where there's more and more automation and less people around to actually, frankly, that want to go out in the whoop and do work out there, we actually have to get all these sensors better. You know, and so, yeah, it's a tough challenge. Yeah.
But in relation to the comment, yeah. the minerals the value chain from resource to metal,
yeah,
is one of those processes where you can only do as well at one point than you've done in the previous steps in the chain, pretty much.
Yeah. Yeah.
All right. So I think that's what the whole idea is to be able to sort of, I'll use the word tag. Tag, well, we know this material's coming through our processing plant at the moment. This is how it behaves, and this is the best we can do. hand on heart, best we can do. That came from this spot in the ore body.
Yeah.
That's remembered.
Yeah.
Whenever it gets another block that's similar to that, we can tell the plant we've got some of that coming.
Well, that's so I'll overbloat my self-importance here a bit, and the work that my team has done over the last, really since BHP had WMC, had a lot of ideas about it, but BHP gave us the resources to do that. If something goes wrong in the plant these days, it's because we've screwed up the process. It's not because we didn't know what the ore properties were. It's not because we didn't know what the recovery properties were. It's because something broke or we did something we weren't supposed to do. So that's a very privileged place to be in. We would dearly love to make things better and better sense stuff, but we're lucky on that side. Does that mean that we can't do better? You bet we can do better. You know, and for us, because we actually have to drill so much, anything we could do to improve that will make a big difference. You know, and getting that information up front, for us to have instantaneous or possibility to instantaneously feed back to the block model and change the block model, I have a difficulty understanding how that's actually going to help us, because what you don't want is your mining people or any process to be going up and down like this with the ebbs and flow as minor changes are happening. You have to wear that out. But often we don't know until we actually start doing it, you know?
So in most conversations I've had with you and many people at OD over the years, it's like, God knows how many ore types there are, you know. But you've clearly been able to sort of group those into a smaller number of, if you know?
No.
In order for the plant to still run pretty well?
What we're able to do, and different than...
I'm not talking blending here.
Yeah, no, but don't say bugger blending. But blending, that's important. What we were able to do a long time ago, because the complexities of trying to integrate all kinds of different parts of the plant together and trying to figure out how we can characterize, we did not have the luxury of the time to develop real... predictors, and recognizing that all of our our metallurgical recoveries were not additive properties. So we could not wait for the geostat side to catch up into that space. We had the unique ability to tag everything back to the single drill hole assay. Besides all the chemistry, the mineral, we measure the chemistry. We predict a large amount of mineralogy, and we can predict everything. We can predict full value chain back to every single drill hole assay or every single meter in that model. But what we do is then we build those up to bigger and bigger blocks. So every block that we move through that plant, or when we decide we're going to move it, we know what's going to cost us to recover and what we're going to get out of that. And that actually gives us a good opportunity to actually do better with it, but we tag it back to that individual, we tag it back all the way back to the beginning of the process. And that's uniquely different than what everybody else is chasing. And I think we get lost a little bit along the way, but we were able to be simple, because the deposit might be complex, but the mineralogy is relatively simple, and we were able to develop those relationships. So, yeah.
If I understand the question, it's really about having the equivalent of an integrated simulator or a digital twin or whatever. I would hope that the projects from PRIF don't just stop there. There is an enormous opportunity to bring forward into the training centre the outputs from those projects. And somewhat ambitiously, one of the PhD projects was effectively to construct, after the event, a digital platform. We also have free access to the integrated extraction simulator, which is another way of looking at it. And of course, we have the Dassault system as a contributing partner. So it's a conversation I'd like to keep going, because that is one element that we need to address. At the moment, because of COVID, we've had significant difficulties in appointing students to the HDR projects. We've still got one that shows no chance of finding anyone in the short term. But by October, we'll have all but that one, I hope, filled. possibly a second one. I'm a bit more hopeful about that. But I think we really would like to start to begin to look at something like support from industry partners to build something like that you're talking about, whether it's the integrated extraction simulator, whether it's a digital twin from your company, or the combination of the two is something we can work through. And I think that would be a very good way of bringing forward projects from PRIF to interface with what we're doing in the training centre.
Peter, can I just want to comment. I could say from our perspective, from BHP's perspective, and I'd say the other big companies that actually have the resources, they're trying to do a lot of that internally already. You know, so think about your value proposition off of that, but it's still a very good idea, but they have the resources to do that, and they know that that's the way of the future. So tap into their things that they're already working on it in the background.
I don't think we ever intended to develop our own digital twin, but it is an integrated operation for complex resources, and the projects are constructed not to be independent of one another. It is a completely interdependent set of projects, and we need some sort of a platform to ensure that that interdependency is maintained.
Hang on, Chris, we just need the microphone so the online audience can hear.
I know that Anglo-Americans using the IES to integrate their mining operations and feed it forward into the concentrator. A lot of the models that are used in the IES are empirical models developed for the crusher or the mill. I'm not quite sure about mining because they just tend to mine anything that's not necessarily ore. But again, I'll back up what Kathy's saying. In terms of the concentrator, particularly flotation plants, we just don't have the sensors to be able to build a robust, reliable, predictable model. You know, what you get today is might have the same elemental head grade, but the mineralogy might be totally different, which means the chemistry is going to be different and you're not going to get the same grade and recovery. Without putting that chemistry spin on things and getting the sensors to measure those things, the models they'll work for a little while and then they won't. And nobody will know why, and then they'll go do a whole lot of regression models, and all of a sudden we've got something that works, but we don't know why. And it's because the chemistry's not being measured. And that get those critical sensors right, then we're in business.
Maybe one last question from Max.
It's not a question, it's just a comment. And I totally agree with Chris. And my comment is one of the things that probably hasn't been said so far, but it is underlying everything. One of the very good things of the PRIF has been taking students and researchers from areas like mathematics or computer science to the mine site and have a look at what they're dealing with and what it looks like. Because on paper it may seem easy to model something like that, but when you realize complexity and heterogeneity of a mine and a mineral processing plant, you realize it's not straightforward, and there are a lot of missing measurements, missing variables. And Chris knows very well, in the 90s, it was very popular in Chile. Everyone was doing flotation modeling, being based on fundamental equations, which are working just for spherical particles in vacuum, and it was nonsense. So building a digital twin of a flotation plant it will eventually happen, but it's really complicated. It's not like car manufacturing. You are dealing with a slurry with particles, which are all different. Every ore behaves differently. There is a lot of chemistry happening. And it's very good that all these mathematicians have had the chance to walk over there and have a look how the real world is. That was a good point for the PRIF.
I think the reverse has been true too. I think I didn't think. Did you think, Bismarck, you'd be using all kinds of amazing mathematical models and algorithms?
So far, it's just the machine learning stuff because those algorithms are able to capture the complex relationship that exists between the various variables as compared to the existing techniques that have been used, like the first order kinetic approach and those mathematical models. So the way forward is the machine learning stuff, but now the main idea, the main challenge here is that it's very difficult to explain to the industry that we have a black box model. We don't actually know the equation that links the various input variable, but it works.
I know a mathematician that can help you with that.
But that's actually, it's an important point, because in industry, sorry, just add on a little bit. In industry, even though I'm a scientist, you know, and I'm a scientist that works in the industry, sometimes the empirical observation, and if it works, that's good enough, you know? And it becomes a luxury to actually understand the underlying reason. And in the long term, it definitely helps you to understand the underlying reason, because you do have a lot of heterogeneity, you know, and it's changing all the time. It's doing this, and when you have, you know, probably 150 different parameters you have to look at, it's difficult. But it actually, sometimes the observation itself it's all that we actually have time to deal with, and then to act on that observation, and you don't know the underlying fundamentals, but it's really important, you know, the stuff that you're doing. So.
Okay, I believe Tatiana has gifts for our panel members. Yep, surprise.
Hey.
Thank you to everyone who. Thank you to everyone who joined us today, both face-to-face and online. Thank you for sharing and celebrating the PRIF Mining Consortium achievements. And I'd like you all to help us celebrate by joining us for networking and drinks in the foyer, and hopefully continuing these wonderful conversations.
Thank you. Before everybody disappears, I'd also like to thank you, Ruth, for being such a wonderful MC today and keeping everybody, I won't say to time, but to keep people reasonably in check. And thanks also to Tatiana for doing all the behind-the-scenes organisation for today, sending out those hundreds and hundreds of emails, reminders, and everything else that we've all received over the last couple of months. It would not have worked today without your fantastic efforts. So thank you very much indeed.